Next, I invite Prakash Rout from BARC, and he will tell us about what you can do and what you can learn about nuclear astrophysics.
Very good evening to all, and I thank the Academy for giving this opportunity to discuss about the underground science facility for nuclear astrophysics. So I will be speaking on behalf of nuclear astrophysics community in the country. We have planned to do some kind of measurement which is importance for nuclear astrophysics. This is the plan of my talk. So I will give what is the basic physics interest and what are the important reaction for the astrophysical interest at the gamma energy and where the cross section is very small and why we need to go underground. And we have proposed one 5 MB accelerator for this kind of measurement. And then I will tell to what are the other additional equipment required to do very sensitive measurement, then I will summarize. So already Basu told that what is the cosmic reduction and then how much one can go if you go to deep underground. So if you see the nuclear astrophysics is the physics which connects nuclear physics and astrophysics. And to understand the origin of elements and the stellar energy production, and this requires the nuclear data and also the decay rates, which is responsible to understand the various stellar nucleosynthesis and evolution. And this low rate needs to reduce the cosmic ray background and the ambient natural background. And this makes the measurement required to go for the underground. If you see the gamma spectrum for high purity germanium detector between surface and underground, so this is the typical spectrum. So it shows that if high energy gamma rays, so above the ground is 0.5 counts per second, and here if you see the rate as we go underground, you see the drastic difference. So the about 10 order of about 10,000 factor reduction is there. And if you see the typical example for the underground laboratory at Gransa, so versus surface for different particles, which is the one is muon, is the factor of 6 reduced, and for the neutron and gamma rays also the natural backgrounds and which can be which is reduced by the thousands and maybe depending upon energy it is maybe 10,000 or more. So depending upon the this kind of in order to measure the low cross section, one has to go to underground cases. So if you see the cross section and for the charged particle to fusion, so this cross section is very small, and above if you below the Coulomb barrier, so the cross section reduce exponentially. So and there is a so-called S factor which is used in the very many stellar nuclear stellar model for the prediction of the stellar nucleosynthesis and evolution. So this is the taken care the energy dependent part is almost constant. But if you go to the gamma energy, where this shows that where the reaction takes place at the high energy part of the this Maxwell distribution, and this was the tunneling probability as a function of energy. So here the gamma energy, this is the maximum reaction takes place, and this is the energy where the cross section is required, and this is very small, and if you the order of magnitude small, and if you see the typical reaction which is interest of different processes. So one is this radiative capture gamma alpha is a carbon gamma alpha gamma, and which is gives which is important for the massive stars. And if you see the cross section is very small, It varies from the different cross section which is of interest is from minus 33 centimeter square to minus 41. So wide difference, and the gamma energy is very small, from few tens of kV to hundreds of kV. And this is the processes which is relevant to study the massive stars, and what is the abundance of the fluorine, and what is and also aluminum 26. This is magnesium 25P gamma reaction. This is for to understand the what is the rate of this aluminum 26. And these are this cross section is measured from the different labs. And if you see the error, the huge, the precision is very small, and their error is quite a bit. So this kind of measurement, the gamma energy is very small, and the cross section is less than few tenths of femtobarn. So this is very tiny cross section. To measure you required to have the deep underground laboratory. And in addition, so what we think that if you see this kind of measurement, this is relevant for the different kind of environment, different temperature, and the different temperature. If you see this one, carbon fusion reaction. So for the massive star, the gamma energy very small. There the no cross section is data is available. So these data are very important for the constraining the stellar model prediction and the model calculation. And these are the called holy grail in the nuclear astrophysics. And this is what is the carbon to and oxygen ratio in the universe. And this a lot of data is not available where the gamma energy is there. So and also this is the alpha n. This is the neutron production in the universe where so these are responsible. This kind of neutron source are responsible for the production of heavy elements beyond iron in the different astrophysical environment. So if you see the rate, the yield of this, so it depends upon the projectile and target of the thing, and also the cross section. If you consider the very small cross section in the femtobarn or cross section, and even if the gamma rays, the detection is 10% or to 15%, and but the charge particle is 100%. So using that, one can see a very low cross section is required longer time, and so to have the sizable detection, the statistically significant detection. So if the no data even in the near gamma energy is there, if some cases is few exceptions, some is there. And so in order to do such kind of measurement, we propose to have a few MeV machine. So and also to study, to go to very low energy, we use the inverse kinematics and covering wide range of energy. And in addition, so we want to have also to have some RMS to further reduction of the background. So this is proposed from the community. So that initially phase you have to have 4 MB high current oscillator with ECR ion source, and this proposal will take few years for the installation. And parallelly we also work on the 5 MB machine. So using these two system, one can cover gamma energy to up to high energy, so by different technique. So these are the two, the cavern size is required 20 meter by 20 meter as, and typically it's 10 to 15 years. But the cross section which is still is very important to measure, and each energy or each cross section takes to 5 to 10 years of the data to do the, so still it will be very important to do such kind of measurement using So these are the few things but this requires some indoless gas target, which is already, so in order to have very low cross section or gamma peak, we require very high density target, gas target. So this is proposed that typically the gas target when you couple to the beam, so this is the high vacuum system, so you have a differential pumping, and then you have a RMS, so that make a coincidence with the detection system, we can further reduce the background. So you can have a significant reduction of the background. So if you see the typical intensity of the different processes, so the background, so the mu1 can be reduced if you have a deep underground, But in addition to the other beam-induced and other natural background, one can reduce further by using the RMS. So the lab underground is required. The precision is limited by the natural and beam-induced and the target. And this is RMS with inverse kinematics. So with the gas jet target. And the proposed underground laboratory can dramatically improve the sensitivity and accuracy and reduce the systematic error, the different reaction I told. So we have already worked on this advanced gas jet target with the RMS system, so that this can be used, this kind of gas target, helium and tritium and hydrogen. So these are the very expensive gases. So it required also recirculation. So one can have very good purity, maybe more than 99%. And this RMS can eliminate the beam-induced and the natural background and the target impurities. So this design with very compact, so that one can place in the small cabin, so along with the accelerator, so one can do the world-class measurement. So so if you see if I summarize, the major opportunity exists still to understand the helium and carbon burning reactions near gamma energy. It's very so these are the gamma energy for the different stellar environment is different. So the proposed accelerator, high current accelerator, can scan the different reaction at the different gamma windows. And the deep underground accelerator facility allow us to perform the world-class low background nuclear astrophysics experiment, and this will constrain different model, the stellar model or nuclear synthesis, understanding the all these elements, how it is produced through different channel, so it can be addressed. So initially the 4M100 kV front end and with 5 MV high current machine is required for this kind of facility, and together with the low the recoil mass separator and windowless gas target system. So this will be unique facility to study the nuclear astrophysics and measure the different kind of cross section relevant for the nuclear astrophysical phenomenon. With this, thank you for your kind attention, and I thank you.
Thank you, Prakash.